All right, guys, are there any questions over any of the assignments so far? Any questions over any of the assignments we've done thus far? Okay. Now, the first thing I have up here is simplest form. Now, we went over these and had these yesterday. In simplest form, no radicands have perfect nth powers as factors other than 1. So what they're saying is that we can't have, say, 2 to the 4 halves. We can't have it so that we can actually pull something out or simplify. No radicands can contain fractions. And no radicals can appear in the denominator of fraction. So what we kind of talked about yesterday. Now, one of the properties that we do have that we're kind of adding is this here, these multiplication properties. And what we're saying is that the nth root of a times b is equal to the nth root of a times the nth root of b. We can split them apart. We can also do the same thing for division. That the nth root of a divided by b is going to equal the nth root of a divided by the nth root of b. And we can go back and forth with these here depending on what's going to help us solve these better or easier. Because if we have two that are split up and a and b are both divisible, we can divide them evenly. Then we'll want to put it back together. If they don't, then we'll want to split them apart so that we can actually be able to simplify it. Because like this example here, well, 162 is divisible by 2. So if we actually put them back together, having a fractional expression inside the radical, well, 162 divided by 2 does give us 81. We don't have a fraction anymore, and we can simplify from there. So, if we look at the first one here, we have the cubed root of 12 times the cubed root of 16, or cubed root of 18. Well, the first thing we can do is actually just multiply these together and say that we have the cubed root of 12 times 18. Now we can go on and multiply 12 and 18 together. And if we do 12 times 18, 6, 2016, 216. So we get this here. Now we just need to see if we can take the cubed root of 216. And we can do that either by calculating and see if it does come out evenly. Because if it does, awesome. If not, we have to do this by hand and actually calculate it out. And if we calculated this by hand, well, 216, since it's an even number, we know that it will be divisible by 2, which would be 108, which is still divisible by 2, which does give us 54, right? Because if we did the factor tree, well, we can get all the way down to 27. We good to getting there? Well, 27 is divisible by 3, 3 and 9, which is 3 and 3. Well, we have 2 3 times, yes? So it's really saying that inside here we have 2 to the third times, well, 3 appears 3 times. Well, the cubed root of 2 to the third is 2. Cubed root of 3 to the third is 3, and 2 times 3 would give us 6. So for this one here, it does work out to be a whole number, but we can do this here. Any questions on this here? Okay. Any questions on A before we look at B? Now, when we look at B, we do have a radical in the denominator. We have two radicals actually being divided. And since they both have the same index, we could merge them back into one. But the real key to being able to do that, or actually wanting to do that, is looking to see, are the numbers inside the radical actually divisible? Will 80 divide by 5 evenly? Well, yes. That is the main key for us wanting to put them back together. Because if 80 didn't divide by 5 evenly, we're going to leave it as this here and try to see if we can simplify the radical out of the bottom of this fraction. But since these do divide evenly, we can use this division property to put them back together. To say that we have the fourth root of 80 divided by 5. Well, 80 divided by 5 is 16. So at this point here, we need to see if we can take the fourth root of 16. Well, yes. And it is 2. Because if we looked at the factor tree, because it'd be 2 times 8, which is 2 times 4, which is 2 times 2. We have 4 2's. Any questions on this here? Not always, no. Because we're doing these with some that work out nicely because it does give us a basis for understanding this principle and how it works, as well as giving you guys a way to actually being able to check your answer to make sure you did it right. Because once we start hitting the ones that don't or hitting variables, we can't just plug it in to see if we got the right answer. Any other questions on the first two here? Okay. Now the next one we have the third root of 4 times the third root of 128. Well, we can't take the third root of 4 and get a nice even number, and we can't take the third root of 128 and get a nice even number separately. But our multiplication property says that this is also the same as the cubed root of 4 times 128. And well, 4 times 128, 2, 512. And if it does work out nicely, and we could take the cubed root of 512 and see if we get a whole number, we could do that. And it'll work out to actually give us what? 8. Because we could have also looked at the factor tree, breaking it down and simplifying it that way as well. Any questions on these here? All right. Let's look at B. Well, with B, we do know that 192 will divide by 6 evenly. So what we can do is actually rewrite this as the fifth root of 192 divided by 6. And 192 divided by 6 actually works out to be 32. And at this point here, we are looking at the fifth root of 32, which is 2. And again, for 512 or 32, we could have used a factor tree to break it down to see what our numbers would be. Any questions on this here? All right. Let's look at the next one, the cubed root of 135. And I think at this point already most of y'all have at least tried to take the cubed root of 135. And did you get a whole number? No. So we need to look at the factor tree of how this simplifies down. Well, one number that I do know that will go into 135 is 5. And 5 goes into 135 27 times. So 5 won't go anymore, so there is one number that won't simplify out. Now 27 would be 3 times 9, and 9 is, well, we do have 3 3's. So we're saying that I have the cubed root of 3 cubed times 5. Now, according to the multiplication principle, we really have that we have the cubed root of 3 cubed times the cubed root of 5, because I can split that multiplication up into each individual term. And we know that the cubed root of 3 cubed is 3, but that will simplify. Will the cubed root of 5 simplify? Well, no. So we're left with 3 times the cubed root of 5. And that there is our final answer. Okay. Because the 3 did simplify up, but because the cubed root of 5 didn't, we can't simplify it all the way down. The yellow calculators are very helpful in doing this with square roots. It doesn't like anything higher than a square root. So it doesn't deal with cubed roots or anything higher than that. Now, let's look at B. We could try plugging this in, but again, it's going to give us a decimal. So the ones moving on from there, if we looked at this here, so division, on the last ones we did, we combined them into one, where we had the 5th root of what would be here 7/8. But does 7 divide by 8 evenly? Well, no. So there's not any real point to sticking them together because it doesn't help us. And the main focus and the main issue that we have with this is the fact that we have a radical in the denominator. We can't have this 5th root in the denominator, mainly because we're really saying that we're dividing by an irrational number, a non-repeating, non-terminating decimal. Let's go back to the calculator pen. Am I able to rewrite 8 as a number to a power? Is there a number that multiplied by itself a certain number of times would give us 8? Well, we can look at 8 is 2 times 4, and 4 is. So 8 is actually the same as 2 cubed, yes? So in the denominator, we can say that we have the 5th root of 2 cubed. Can we take the 5th root of 2 cubed? No, because we really need it to be what? 2 to the 5th. Because if it was 2 to the 5th, well, the 5th root of 2 to the 5th would simplify. Those would cancel out, yes? In the numerator, we have the 5th root of 7, yes? Well, as we just said, if that was actually 2 to the 5th, not 2 cubed, we wouldn't have a radical in the denominator anymore, correct? Well, how many 2's am I short? 2, yes? So, well, if I can multiply it by 2 squared, we would get 2 to the 5th, yes? But I can't just multiply it by 2 squared. It has to be what? 5th root of 2 squared, because we need them to both have radicals. The only way we can multiply 2 radicals is if they have the same index. So 2 to the 5th. So the 5th root of 2 squared would multiply together to give us what we want. But we also have to do it in the top as well. And for us, the denominator would be the 5th root of 2 cubed times 2 squared. The numerator, we would do the same thing because since they both have the fifth root, we can multiply what's inside, which would be 7 times 2 squared. Any questions on this here? Now the denominator is the fifth root of, well, 2 to the fifth, because we would add the exponents together whenever we're multiplying like bases. And I mean, that's what we expected. That's why we're doing this. We needed the denominator to be the fifth root of 2 to the fifth. Yes? Now, the numerator, do 7 and 2 have any like terms? No. Because if they did, I mean, originally we could have actually divided. We could have simplified, yes? So here, I'm going to go on and square 2. Realistically, we could say 7 times 2 squared and go on and simplify that. Because, well, since 7 is prime, and we definitely don't have enough 2's, because 2 squared is not going to simplify the fifth root, we can go on and just start multiplying those back together. Because if it doesn't simplify in the root, we don't have to have it in this broken down form. So really, so the numerator, 7 times 4 is 28. Fifth root of 2 to the fifth is, so that there is the final answer. And the only way we'll most likely have something that's simplifiable in the numerator is if it's simplifiable to begin with. If we could have taken the fifth root of it to begin with, then we could have simplified it. Questions on this here? And again, one of the biggest things with this problem is making sure, okay, at the start, the fifth root of 8, we want to make sure that we rewrite that as a number to a power to start with. Because if we just went on and multiplied it by 4 roots of 8, or the fifth root of 8 to the fourth, it would give us an issue because we're adding more than what we need. Because if I did that, 8 to the fourth, 5, 8 to the fourth, well, this is 2 cubed to the 4 fifths, which would be 12 fifths. 12 fifths is the same as what? 2 and 2 fifths, yes? Well, I added an extra factor of 2 twice to the top and bottom, which means at the end, I would have to take those extra factors of 2 out of the top and bottom, and instead of getting this here, we would actually gotten 4 times the fifth root over 8. We have to factor it right back out. So whenever you're doing this multiplication and working this through here, well, I won't scroll. Whatever's inside of here, the power for 2, or the number inside there, shouldn't be bigger than whatever the root is, because that means we're adding more than 1 to it. All right. And since we're thinking about those there, why don't we go on and look at B, because that'll be a little bit helpful since we're still thinking about those there. And the number itself, so the cubed root of 500, isn't as bad as the fraction. So, looking at B here, there's a few things we need to ask ourselves. One, is 19 and 4, are they divisible? Well, no, we can't divide 19 by 4. Well, 19 is prime, yes? The only factors are 1 in itself. So, 19, there's nothing we can do with it. We definitely can't take the fourth root. We can't take any root of 19 and get a whole number. But now we need to look at the denominator, our 4. Can I rewrite 4 as a number to a power? Well, yes. 4 is what? 2 squared, yes? And we need this because it's telling us instead of just having 1 4, we actually have 2 2's. And if I want to take the fourth root of it, I need to not have 2 2's, I need how many 2's? 4, yes? Well, how many am I missing? 2. So here, I'm going to multiply the top and bottom by the fourth root of 2 squared. Because doing these here, it's really finding what is the next exponent. How many more of that number do I need to get to the next exponent that would simplify evenly? So here, the next one would be 4. And if we had not 2 2's, but 3 2's, we would only need 1. Well, if we had 4, we'd be not having to worry about this. But if we had 5 2's to start with, well, we wouldn't be looking at 4, we would be looking at 8, because we're looking at the next set of 4. What is going to be the next set of 2's that we would need to get that radical to go away? So we're looking at 4, 8, 12, 16, 20, any of those multiples of 4. Here, luckily, we only need 2. Now for the denominator, we could go on and do like we did on the last one and say this is the fourth root of 2 squared times 2 squared. Well, 2 squared times 2 squared is just going to be what? 2 to the fourth. That's why we're doing this. That's why we're multiplying it top and bottom by 2 squared, the fourth root of 2 squared. Now the numerator is going to be the fourth root of 19 times, well, 2 squared. Well, we know the fourth root of 2 to the fourth is just going to be 2. Now, as we said already, 19 is prime. So there are no common factors, because if there were any common factors of 2, so if 19 had 2 more 2's as factors that we multiplied in there, okay, now I have a total of 4 that I can pull out. But we don't. 19 is prime. So really at this point here, we just need to do 19 times 2 squared, or 19 times 4, would be 6. I want to say 76. And that would be it there. Because we could try to see if we could take the fourth root of 76, but we can't, because 2 squared is not enough 2's. We need 4 of them, yes? 19, if it had any products of 2, I could break it down to 2 times a number. Then we could pull something out, but prime, 19 is prime, so this is as far as we can take it. Any other questions on this here? Okay. Let's look at A, the cubed root of 500. Well, with these here, again, we could do factor trees, because most likely 500 is not going to be divisible, or we can't get a whole number if we take the cubed root of it. Well, we can do our factor trees, which we can say, well, 5 and, I can do 5 again, 20, which is 5 and 4, and 4 is, we do have 3 5's, yes? And how many 2's? 2. Do I have enough 2's for this to simplify the cubed root? No.
So would this not work if we skipped one of them? So if we started at like 5 way down?
Yeah, no, no matter how you do it, as long as you break it all the way down, you'll get there. Because if you did, instead of 5 for 100, 5 and 20, you did 2 and 50, that would still work. We'd still get there eventually, as long as you didn't stop too soon. So it's telling us that we have the cubed root of 5 cubed times, well, 2 squared. Well, we know the cubed root of 5 cubed would be 5. And as we said, we don't have enough 2's to bring it out, because we need at least 3, or groups of 3. Well, it's going to stay inside. And I'm not going to leave it as 2 squared, because 2 squared is 4. because anytime it doesn't come out as a number, we just rewrite it back to what it should be. We don't leave it as an exponent. Any questions on this here? And as you've noticed with a lot of this here, it's really manipulating these numbers so that we can get it back to whole groups. We're trying to get to whole groups. Now this here, we've done these before, but not with radicals. We've done them with complex numbers. Because if you remember having 1 over 5 minus I, to get rid of the I, just like what we'll do with the radicals, is we take what the denominator is and change the sign in the middle. So if it was positive, it's now going to be negative. If it was negative, it's now going to be positive. And what we're using here is not the complex conjugate, it is the irrational conjugate. And if we multiply these together, well, the numerator, we're multiplying our 5 minus the square root of 3 by 1. Which is just going to work out to be 5 minus the square root of 3, because that's one of the nice things about multiplying with 1. Now the denominator, we're going to have to distribute this out. So we're going to do 5 times 5, which is 25. 5 times negative square root of 3 is negative 5 square root of 3. Positive square root of 3 times positive 5 is plus 5 square root of 3. Hey, that's kind of nice. And lastly, square root of 3 times negative square root of 3 is, well, negative square root of 3 squared, or we can say negative square root of 9, because the 3 times 3 would give us 9. Either way we look at that, it'll turn out to be the same thing. Numerator still 5 minus square root of 3. Our middle terms, the negative 5 square root of 3 and 5 square root of 3 become 0. Because if we add or subtract, it would become 0. So those are gone. We still have the 25. Minus, what is the square root of 3 squared? Because really what we're saying is that I have 3 to the 1/2 squared, which is 3 to the 2/2, which is 3. Well, last but not least, 25 minus 3 is 'cause we had 1 over 5 plus the square root of 3. 1 over 5 second square root 3. If I can type that in right, let's try again. Fraction 1 over 5 plus second square root 3. That's the exact same thing, isn't it? Well, almost, except it put the square root in front instead of second. Same thing. I liked having the radical second, but it really doesn't. Because if you wanted to, when it gave you that as negative square root of 3 plus 5, you can rewrite it as 5 minus the square root of 3 pretty easily. Just switch the two numbers, making sure you keep the signs. So here, we can say 1 over second square root of 7 minus 1. So the calculator told us this one, well, square root of 7 plus 1 over, it should be, square root of 7 plus 2 over 3, yes. Because I did 1 instead of 2. Yeah, square root of 7 plus 2 over 3. If I typed it in right. Or we could say 2 plus the square root of 7 over 3. Because those will be the exact same thing. And this works as long as the radicals in here are all square roots. Because if we get cubed roots, then we actually have to do this by hand. And it'd be a little different. And it'd be a lot harder to get rid of the radical, because this really only works with square roots. Because it's really based off, all of these here are based off of our, the difference of perfect squares. Because our a minus b times a plus b, if we expanded this, is our a squared minus b squared. Because whenever we square a radical, the square root and square would cancel out. That's the principle behind why this works. Whereas some are difference of perfect cubes, so a cubed plus b cubed does not work out that nicely, because we end up getting a plus b times a squared minus ab plus our b squared. We don't get that nice form. We'd also have to figure out what this radical is. But the rest of these here, if we wanted to do them in the calculator, we could. Because even this one here would work. But that's it.